Hi everyone, my name is Leland Dorchester. I'm a Master of Science student in the Hydrologic Science and Engineering program. And right now I'm going to be talking with you a little bit of a method for improving predictions of solute transport in groundwater systems by incorporating pore-scale processes. So before we get started, I thought it could be useful to define a few key terms that are relevant to my research that some of you who might not have as much of a geologic background might find useful. So the first of these is the term porosity, which can just be defined as the volume of voids in a rock divided by the total volume of the rock. And so porosity can exist for a variety of reasons, which are shown over here on the right-hand side. But what's relevant in my research is that porosity exists in the presence of granular material. And for the purposes of my research, I actually differentiate two different kinds of porosity. These are called the mobile porosity and immobile porosity. And the mobile porosity can just be defined as the fraction of rock which easily transmits solutes or groundwater through a groundwater system. And the immobile porosity can just be defined as the fraction of rock which does not easily transmit solutes in a groundwater system. So then we have this term mass transfer rate, which essentially serves as a link between the immobile and the mobile porosity. It just describes the rate at which solutes or mass moves from the immobile porosity to the mobile porosity. And it's actually the incorporation of these three terms that serves as the basis for what is known as dual domain mass transfer modeling. And this is the dual domain mass transfer modeling is a technique that my researchers build on and is just a proposed alternative for more traditional methods such as the advection dispersion equation. And then lastly here, we have this term hysteresis, which is a little bit of a weird one, but I'll get into it in a little bit later. But for now, let's just define it as a time-dependent event in which the measured value of a physical property lags behind changes in that physical property itself. So here what we're looking at is two concentration breakthrough curves. On the left-hand side, we have a concentration breakthrough curve under conditions that are used in the advection dispersion equation. And then on the right-hand side, we have an example used in dual domain mass transfer modeling. And so what's important to know is that more traditional methods, like the advection dispersion equation, are essentially idealized because they operate on some overarching assumptions, which may or may not necessarily actually be good assumptions. And one of these assumptions is that we are working in a homogeneous groundwater system. And so for those of you that might have a little bit more of a geologic background, you might recognize right off the bat that assuming homogeneity is not necessarily always the best assumption that we should be making. And that's because I would argue at least that most, if not all, Earth materials are going to incorporate some degree of heterogeneity. So anyways here, on the left-hand side, if you were to assume homogeneity and work with one of those more traditional models, such as the advection dispersion equation, you would see that contaminant spreads in a nice homogeneous fashion. So we'll have the same amount of spreading on the front end of the plume as we will on the back end of the plume. So we can see that graphically here on these concentration breakthrough curves, which create a nice Gaussian shape. On the right-hand side, we have something that might be a little bit more realistic, where we can see this includes dual domain mass transfer properties in their model. And we can see that the concentration increases rapidly. It doesn't always, but in this scenario, it does plateau. And then you can see that the concentration actually slowly decreases. And the slow decrease in concentration versus the more rapid increase in concentration insinuates that there might be some degree of heterogeneity within our groundwater system. So these dual domain mass transfer models have actually been around for quite some time, and they have been shown to be more accurate representations of homogeneous groundwater systems and heterogeneous groundwater systems. But the issue with these dual domain mass transfer models is that historically, they're just difficult to define. And that's because in order to build them, we need to find some way to access the immobile domain. And typically that's just done with some back calculations, which can be kind of difficult. So that's where geophysical techniques come in and can be really handy. One technique that I work with in particular is called electrical resistivity. And that can just be, for those of you that don't know, that can just be thought of as studying how electrical currents move through a geologic material. So by coupling electrical resistivity with fluid sampling, we can actually begin to look at the relationship between the fluid conductivity of a groundwater system and the bulk conductivity of a groundwater system, and begin to tease out the relationship of the immobile and mobile porosity. So that's kind of what we're looking at here in this top right figure, where we can see that the fluid conductivity and the bulk conductivity versus time have both been plotted, but look slightly different. And then down here below that, a really useful technique is to actually plot a time series data of the fluid conductivity versus the bulk conductivity. So in a system which shows dual domain mass transfer properties, you'll begin to see hysteresis, which is what I was defining for you earlier. It's kind of that weird term. And this is what it looks like graphically. So this right here is actually the model domain that I'm working with. It's important to note this is a completely theoretical model, but it is defined as a 2 centimeter long by a 1 centimeter wide porous media. The white circles represent impermeable grain, so this might be something like sand, for example, and the gray area represents the pore space in the model domain. And on the left-hand side, we have the inlet, which serves as the area where groundwater flows into the model. Solute is injected, and it serves as the electrical current source. And on the right-hand side, we have the outlet where water flows out, solute flows out, and it serves as the electrical current sink. So this is what the model looks like when it's up and running. This is just one snapshot in time out of many. And what we're looking at here, we can see solute is injected on the left-hand side, flows from left to right, and red indicates areas of high concentration, blue indicates areas of low concentration. And we can see that that solute actually seems to be following what looks to be like a high velocity zone, and is taking a little bit longer time to move in low velocity zones. So for example, those high velocity zones can be seen in the upper and middle right portions of the aquifer. And it's important to note that this model is built to mirror a pre-existing model that looks almost exactly like this. And the authors, whose names are Leland and Heterogeneous, were able to build a dual domain mass transfer model. But the important difference between my model and their model is that my model uses direct measurements of electrical resistivity, and we will hopefully be able to create a dual domain mass transfer model from that. And so this is just a handful of preliminary results. We don't need to go too much into the details, but what's really exciting to see here is that we are seeing hysteresis. So each one of these curves corresponds to a red dot on the right-hand side of the screen. And as you might note, at some locations within the model, we're seeing stronger trends in hysteresis, and in other areas, we're seeing weaker trends in hysteresis. And something that remains to be understood is why we're seeing those different relationships. You may have also noticed that hysteresis is proceeding in clockwise directions at some areas, and in some other areas, it's proceeding in a counterclockwise direction. And so that's just some further work that we have to do. But really, at the root of it, this is just really exciting because it shows that even though we're working in a homogeneous model, we still are able to see dual domain mass transfer processes, even at the pore scale. And what I didn't mention earlier is that a handful of studies have been done which have shown we can use geophysical methods coupled with fluid sampling to create dual domain mass transfer models, but these have all been at the field and at the laboratory scale. So what's really exciting about this is that we're able to do this. Hopefully we'll be able to do this at the pore scale as well. And this could have some really large implications for practicing engineers and hydrologists that are working in environmental health and safety and water resources as well. So lastly, moving into this project, we did have some other questions that we wanted to look at. One of these is whether or not hysteresis was still observed in a heterogeneous versus a homogeneous system. If we were to look at a heterogeneous system, that would involve defining an immobile porosity. And for example, that would probably be occurring in those white grains. So then we would have an explicitly defined heterogeneous system that we could be looking at. Another question we had is whether or not hysteresis is dependent on flow conditions, such as whether or not we were working with a fast velocity flow regime versus a slower velocity flow regime. And then lastly, one question that actually came up after a handful of our preliminary results were looked at is whether or not sampling geometry impacted our hysteresis results or our dual domain mass transfer behavior. And this is really important because, as you may have noticed, it looked different at different locations within the model. And so if we can figure out whether or not our sampling geometry impacts what we were looking at, this could have some pretty strong implications for how practicing hydrologists and engineers might design a field study. And with that, that's all I have today. Thank you for listening.